Hello everyone, I'm Q1O, PhD student from the University of Illinois Chicago, and I'll be presenting our work titled Autonomous Dissection in Robotic Cholecystectomy. Our previous work had key limitations: a limited dataset that lacked tissue variability and offline dissection trajectory that couldn't adapt to tissue cauterization, and the absence of grasping, which restricted applications and reduced dissection quality. To address this, we introduced an online boundary extraction for real-time adaptation by expanding our dataset with ex vivo robotic cholecystectomy videos and training advanced models for improved segmentation. Additionally, we implemented automated grasping and pulling with forceps, bringing robotic dissection closer to real surgical performance. We created a new segmentation dataset based on comprehensive robotic cholecystectomy dataset, including ex vivo robotic cholecystectomy on porcine livers performed by various surgeons, and utilize SAM2 like in this example, where after you finish annotating the first frame, SAM2 will automatically segment the rest of the frames in the video. Here we improved the keypoint dataset by designing a unique keypoint structure for each instrument, expanding the dataset with additional frames in the CRCD, and training separate models for each instrument. To obtain the boundary points, the models trained on the new dataset segment the tissues and detect instrument key points from the image. Using these predictions and the generated point clouds, we extract adjacent points between the tissues, the gallbladder skeleton, and the instrument post in 3D space. Applying PCA to the adjacent and skeleton points allow us to define the gallbladder surface frame based on its principal axis. Since the hook is on the robot's right arm, we select the adjacent points on the right side of the skeleton as the boundary points. Additionally, aligning the instrument to this surface frame helps the forceps to grasp the gallbladder effectively and minimize unnecessary contact between the hook's edge and the tissue. Here is the overall system workflow. After post-processing the images, the robot aligns the instrument with the surface between the skeleton in yellow and boundary points in purple to grasp the gallbladder. It then pulls until the tissue is sufficiently stretched, ensuring the stable hold and maintaining robot's boundary detection even after the cauterization. Finally, the robot aligns the hook similarly to the forceps and dissects along the boundary points. Here we compare demos of our previous and current work. In the previous demo, gallbladder deformations occurred once energy was applied. Now with grasping, the boundary remains stable even after cauterization. The online boundary further adapts to these changes, improving the dissection process. Additionally, the speed has significantly improved. The total duration remains nearly the same, despite adding grasping and pulling before dissection.